Welcome to Module 50 in this series of lectures on statistical quality assurance and statistical process improvement. We've been discussing the design and analysis of experiments and have come now to uh, pretty much the last topic in this series of 55 modules. This is the topic of fractional factorial studies, and the last 6 modules cover this, discuss this as sort of the high point of this whole discussion of uh, experimental design and analysis. The basic notion here is that we're going to talk about many factor studies where it's really impossible, practically speaking, to do a full factorial study. If one has, say, p factors, even if there are only 2 levels for each factor, the number of possible combinations of those factors explodes. For example, if one has 10 factors, a 2 to the p factorial already includes 1024 different combinations of levels of those 10 factors, and it's very rare in practice that one could afford to collect data on 1024 different combinations, different setups of a so to speak, of a control panel that has 10 knobs on it, each of which has 2 different settings. So in practice, one can only collect data on some fraction of that complete factorial, and how one does that is the subject of these last 6 modules. We're going to consider rational approaches to both the design. Design amounts to how do we choose which combinations to observe, and then subsequent analysis of fractional factorial studies. We're going to limit our discussion here to fractions of 2 to the p studies. That's all we really have time to do in this fairly quick introduction to statistical experimental design. We're going to begin with so-called half fractions, and that means that instead of considering all 2 to the p possible combinations of 2 levels of each of p factors, we're going to consider only 2 to the p minus 1 combinations. Here is, again, more motivation for this last set of material. It's motivation that says, again, that large P complete factorials are impossible in practice. Here is an example taken from an article by Hendricks in a publication called ChemTech. He considered a 15-factor chemical experiment. Each factor had 2 levels, so we've got factors A, B, C, D, E, F, G, H, J, K, L, M, N, O, P, and the levels are listed for each of those factors. The response variable was a measure of cold crack resistance for a product. If one was going to do a complete factorial experiment in this context, 2 to the 15th, or 32,768 runs of the process at a minimum. That's without any replication at all. That's just running every possible combination of each of those of levels of each of those 15 factors once would be required, and that's just typically not going to be doable. Now, here are some obvious, quote-unquote obvious, limitations of this situation and our objective in this set of modules. It should be obvious before one goes any further, and we're really going to try to keep this in mind, that if one is only going to use a fraction of a factorial, there has to be some information loss relative to what one could know from the full factorial. There's no magic by which one learns things that one doesn't observe, and so one can't do as much with a fractional factorial as one could do with a full factorial. That suggests that there must inevitably be some kinds of ambiguity that follow from this information loss. The objective in this material is to use careful planning and wise analysis so that the information loss and the ambiguity are held to a minimum. Here's a very hypothetical, unrealistic, but instructive example. Here's a full 2 to the 2 factorial layout. So we got factor A at low and high levels, we got factor B at low and high levels. Let's imagine that one is going to collect data for sure with factor A low and factor B low. That is, combination 1 is going to be used. If one then says, well, I'm only going to do half of all 4 possible combinations, I'm only going to collect data at 2 of those 4 corners, which one should it be? Let's think that through for a second. If I collected data with at combination A, that is where A is high, B is low, I'd learned something about what happens when I change the level of factor A for low B, but I learned nothing at all about how things change when I go from the low level of B to the high level of B. Similarly, if I chose B as the other combination of which I was going to collect data, I would learn things about what happens when I go from low A to high B, low B to high B, only for the low level of A. That is, I would know nothing about what happens when one moves from the low level of A to the high level of A. So logic says that if I was going to use combination 1, I should also use combination AB. There, both the level of A gets changed and the level of B gets changed from this initial condition of low A and low B. The problem that then arises, though, is that if there's a huge change in response from low A, low B to high A, high B, one can't really know whether to attribute this to the change in A, the change in B, or to some interaction effect of factors A and B taken together. So the point is that I can't know as much using only 2 combinations as I could know using 1, 2, 3, 4 combinations, and that of necessity introduces some ambiguity in how I'm going to be able to interpret the results, and it forces me to think carefully about how to choose that second combination. Here's another example. This is a 2 cube factorial laid out here, supposing that these are the theoretical effects. So there's a grand mean, a main effect of A at second level, main effect of B, main effect of C, main effect or two-factor interaction of A and B, A and C, B and C, and then the three-factor interaction. You can check that if you do addition of those effects for each of these 8 different combinations, that the numbers written on the corners of this cube are the corresponding mean responses. I've circled here 4 out of 8 of those corners. That is, I've circled combination A, combination B, combination C, and combination ABC. Those 4 corners represent a half fraction of those 8 corners, and it happens to be a very good half fraction. I'm not telling you right now how I recognized those as a good set to choose, but those do constitute a good half fraction of that full factorial if I was going to look at half of 8 corners. To give you a sense of what might be possible here, you might ask the question, let's suppose that I get enough data to pretty much pin down that this mean is 4, this one is 8, this one is 10, and this one is 18. What could I learn then from those 8 means? Well, you might think about asking, well, can I learn anything about an A main effect? Remember that for the full factorial, the A main effect would be the average of this guy, this guy, this guy, and this guy, with the average of all 8 subtracted. Problem is, I don't have all 8 corners. What I might think about doing then is taking the average of this one and that one and subtracting the average of the 4 that I do have. That is, if the main effect of factor 2 at its second level is a right face average minus a grand average is 3, I might consider taking the average of the 2 corners that I do have on the right face and subtract the grand average of the 4 corners that I do have data for. I do know what the means are, and in this particular case, I numerically get the same thing. That is, this half fraction version of the main effect is exactly the actual main effect. One might be tempted to think, wow, I've just got something for nothing. Can I really learn about the A main effect from only 4 corners? Well, to think that one through, we might consider a similar calculation for the C main effect. The C main effect is, for the second level of C, is the back face average minus a grand average. And I might think of comparing the back face average minus the grand average to the average of the 2 means that I do know on the back face minus the average of all 4 means that I do know. And what you find is that the available back face average minus the available grand average is 4, while the main effect of C at its second level used to set this example up is 2. That is, I've got 4 based on the half fraction, and the, if you will, the half fraction main effect is not the same as the overall main effect. So here's a case where I don't get something for nothing. I didn't get back to gamma 2 using only the means on those 4 corners. As it turns out, the general story that's told here is that the half fraction A main effect is in fact the overall main effect plus the BC two-factor interaction. The C main effect, the half fraction main effect, is the overall C main effect plus the AB two-factor interaction. And we were able to recover this, the A main effect, as the half fraction main effect because this was 0. That is because beta gamma 2 was 0. When we tried the same kind of trick with the C main effect, we were not able to recover gamma 2 using only the half fraction main effect because the AB two-factor interaction is not 0. Ultimately what this thing says is that we can't really know from a half fraction 8 things. We can really only know 4 things. And one of those 4 things that we can know is A main effect plus BC two-factor interaction. Another one is C main effect plus AB two-factor interaction. And what the technical jargon for this is that we have confounding, we have aliasing, we have ambiguity. The last thing to note in this first module is that this 4 corners that is, or the 4 corners that are indicated on this picture here are really a very nice symmetric 4 corners. If I collapse that cube front to back, top to bottom, or left to right, I would have a full factorial. What that means is that if any one of those factors actually does absolutely nothing, then the 4 combinations that we've investigated, or that we have data for, or we actually know the means for, constitute a full factorial in the other 2 factors, and thereby would give us everything that we could possibly know.